Good afternoon, everyone. We are Team 41, and today we present the progress of our project Online News Popularity. Our goal is to create a predictive model capable of estimating the popularity of an online article before publication using supervised machine learning and MLOps practices. Throughout this presentation, we'll explain how we structured, refactored, and tracked our entire pipeline, from data processing to model versioning and visualization of results.
Our team is composed of 5 members: Steven Sebastian Brucher, our data scientist who led model experimentation and data exploration; Felipe Gutierrez, ML engineer responsible for the model pipeline and deployment structure. I'm Ana Karen Estupiñan, software engineer in charge of project structure and code maintainability; Angel Ivan Ahumada, data engineer who managed pre-processing, dataset handling, and DVC versioning; and finally, Luis Gerardo Barbosa, DevOps engineer who oversaw automation and reproducibility through MLOps tools.
Our presentation is divided into 5 main parts. 1. Structuring the project using Cookie Cutter. 2. Refactoring and organizing our code for modularity. 3. Applying coding best practices in the modeling pipeline. 4. Tracking experiments, visualizing results and managing models. And finally, 5. Our conclusions and next steps.
To ensure our project started with a clear and reproducible foundation, we implemented the Cookie Cutter data science template. This allowed us to automatically generate a standardized directory with folders like SRC, data, models, and notebooks. It ensured consistency across the team and simplified collaboration since everyone followed the same structure.
In this phase, we downloaded and adapted the cookie cutter template directly into our GitHub repository. This step provided an organized and professional project architecture, one that is easy to replicate for future machine learning projects. You can see here how our directories were distributed: configurations, raw and processed data, notebooks for EDA, and a SRC folder for all the scripts. By automating structure creation, we minimized configuration time and focused on experimentation.
We also implemented version control using Git and GitHub. Our strategy was to maintain the main/master branch stable for deployment, while each member developed features on independent branches. Before merging, we always performed code reviews to ensure stability and avoid integration conflicts. This methodology supported parallel development and created a safe and controlled workflow.
Once the structure was defined, we moved to code refactoring. We divided the code into 3 main components to guarantee a logical and reproducible workflow. 1. Exploración y preprocesamiento de datos, which included handling nulls, encoding categorical features, and scaling. 2. Análisis exploratorio de datos, EDA, where we generated descriptive statistics and visualizations to identify correlations and outliers. 3. Construction and evaluation of the model, including data splitting, hyperparameter tuning, and metric evaluation with R-squared and RMSE.
This modularization allowed us to automate the entire flow, from data loading to model evaluation. Each script connects seamlessly to the next stage, ensuring traceability and reproducibility. Anyone can replicate our experiments just by running the main pipeline without re-executing the notebooks manually.
Next, we refactored the model training logic into a full scikit-learn pipeline. We implemented a custom transformer called Feature Selector, built with object-oriented programming principles, which automatically selects or discards features based on parameters from params.yaml. We then added a simple imputer to fill missing values using the median strategy and a standard scaler to standardize all features, ensuring the model converges efficiently. Finally, we trained our model using XGBoost, known for its robustness and speed.
Our script src/train.py executes this pipeline safely. It avoids data leakage by fitting transformations only on training data, xtrain, then applies the same transformations to test data, xtest. The output, including the trained model and preprocessor, is automatically stored as artifacts, model.json and preprocessor.pkl. These are synchronized and versioned, ready for deployment or retraining.
To make our experiments reproducible and measurable, we integrated MLflow and DVC directly into the pipeline. MLflow automatically tracks parameters such as hyperparameter values from params.yaml, metrics like R-squared and root mean squared error for model comparison, and artifacts linking each model version with its corresponding metrics. This creates a clear history of every experiment we've run.
With MLflow UI, we can visually compare all our runs and quickly see which configuration performed best. For example, changing n estimators and retraining immediately shows if R-squared improves. Meanwhile, DVC controls versioning of our data and models. In dvc.yaml, we define the outputs of each training stage, ensuring synchronization between data, code, and models.
This integration closes the MLOPS loop. Git versions the code. DVC versions the model. MLflow tracks the results. Together, they guarantee traceability, reproducibility, and consistent performance over time.
In conclusion, our project successfully implemented MLOPS principles through every stage. 1. Standardized structure with cookie cutter. 2. Clean modular code through refactoring. 3. Automated pipelines with scikit-learn and XGBoost. 4. Experiment tracking with MLflow and model versioning with DVC. In conclusion, our project successfully implemented MLOPS principles through every stage. 1. Standardized structure with cookie cutter. 2. Clean modular code through refactoring. 3. Automated pipelines with scikit-learn and XGBoost. 4. Experiment tracking with MLflow and model versioning with DVC. In conclusion, our project successfully implemented MLOPS principles through every stage. 1. Standardized structure with cookie cutter. 2. Clean modular code through refactoring. 3. Automated pipelines with scikit-learn and XGBoost. 4. Experiment tracking with MLflow and model versioning with DVC.
Thank you very much for your attention. We are Team 41, Steven Brucher, Felipe Gutierrez, Ana Estupiñán, Angel Ahumada, and Luis Barbosa, and this concludes our presentation for Fase 2, Online News Popularity.